Question 16 first wants to know what's meant by the enthalpy change of hydration. So questions like this are easy in the sense that there's no thinking to do really, these are just things you learn in advance, but for that reason you've got to be very precise. So you can't just say vaguely what it's to do with, you'll get no marks for that. So you've got to make sure as you're doing your revision that you know what these terms mean and can explain it precisely. So enthalpy change of hydration is the enthalpy change when 1 mole of gaseous ions dissolve in water to form hydrated ions. So you've got to get the 1 mole business, and you've got to get the idea that it's transfer from the gas phase to form hydrated ions in aqueous solution. So next it wants us to complete this Born-Haber cycle for the solution of calcium fluoride. So remember, what you're doing in a Born-Haber cycle is breaking down a complex process like formation from the elements, or in this case dissolving in water. You're breaking it down into lots of small steps. And so these aren't difficult to learn because there's a sort of logic to the story of what the short steps are. So in this case they've given you your sort of bearings by labelling this step as the lattice enthalpy. But the overall change is this one, right? Because that's going from the calcium fluoride solid, and we know that's what's down here because that's what lattice enthalpy produces. Remember, it takes the gaseous ions and breaks them down into the lets them stick together to form the solid. So we know that's what's at the bottom, and the overall change is that calcium fluoride dissolving in water to give you aqueous calcium ions. And state symbols are very important in these things. You've got to put every single one in, otherwise you're going to start losing marks very quickly. So aqueous calcium ions and 2 lots of aqueous fluoride ions. So that's the overall change, which is delta H of solution, and it tells us that one is plus 13 kilojoules per mole. So what we're doing then when we break it down into steps is to think, right, if we've got the solid, the first step is that you have to break up the ionic bonds. So you have to convert these ions, which are all stuck together in the crystal, into gaseous ions. And that's just the exact opposite of the lattice enthalpy. So if lattice enthalpy comes down there, breaking up the lattice goes up to there. And so that's going to be gaseous calcium ions and 2 moles of gaseous fluoride ions. And you can see the difference between there and there is just the state symbols. So what we're doing is these are the hydration steps. So first, well, it doesn't really matter which order, but let's say first we'll hydrate the calcium ions. So that's going to take us to calcium 2 plus aqueous. And for the moment we leave the fluoride ions in the gas phase. And then in the second step we hydrate the fluoride ions as well. Okay, so let's put the rest of the numbers on. The lattice enthalpy, it tells us, is minus 2630, so we can put that on here. And the enthalpy change of hydration of calcium 2 plus, which is this step where we're taking the calcium 2 plus ions into water, that's minus 1609. So this is the one we don't know. So let's call that X. And you can see that X is not just the enthalpy change of hydration of fluoride, because there are 2 moles of F minus. So X is equal to 2 times delta H of hydration of F minus. So we can now just compute that, and remember that the way you do that is by putting together a pathway which corresponds to X. Okay, so which starts where X starts and which finishes where X ends. So that means that we've got to go up here first, because that's where X starts, and if we go up here and then down to the bottom and then back up again, because the point is we know the numbers for each of those 3 steps, and the sum of the 3 starts here and ends up there, so that's going to give us the right number. And it's very easy on an enthalpy profile diagram, because if you're going up the page it's a positive number, if you're going down the page it's a negative number. So the first step, it's minus 1609 when you come down here, so it's plus 1609 when you're going up the page. This is the lattice enthalpy, so that's minus 2630. And then coming back up is plus 13. So we've got the numbers for each of the steps, and so we can say that X is equal to plus 1609 minus 2630 plus 13, which is minus 1008. But remember, that's 2 times delta H of hydration. So we can therefore conclude that delta H of hydration is equal to minus 1008 divided by 2, which is minus 504 kilojoules per mole. And therefore that's your answer. Last part of this question wants us to compare delta H of hydration of these 2 ions. So remember, hydration enthalpy is about the strength of attraction between the ions and the dipole of the water molecules that hydrate them. And that depends on 2 factors. The charges on the ions, that's a fairly obvious one. The bigger the charge, the stronger the attraction to the dipole will be. But those have the same charge, and it's worth saying that they have the same charge. But what they differ in is their size. And remember that the smaller the size of the ion, the higher the charge density, if you want to put it that way. In other words, the more attractive it will be because the charge is more focused in a small volume. So they have the same charge, but F minus is smaller than Cl minus. And so the consequence is that F minus is more strongly attracted to the dipole of water. Okay, to the dipole of water molecules. And if there's stronger attraction, more energy is going to be given out when they stick together. And so that means that delta H of hydration is more exothermic or more negative for F minus. Okay, now there's a lot you have to be careful about in the way you word it. In particular, if you say things like fluorine is smaller than chlorine, or if you in any way imply that these might be atoms rather than ions, you're not going to get the mark. So the way to avoid that is use the formulae. F minus is smaller than Cl minus. It's crucial that you include the charge in saying things like that. You've got to get the idea of attraction to the dipole of water in there. That's because that's the origin of the exothermic change. And then crucially, when you come to the comparison, whenever you have numbers that can be negative, like delta H's, or electrode potentials, or entropy changes, or free energy changes, any of these things, you need to avoid saying bigger and smaller, because for negative numbers that's ambiguous. So the way you avoid it is by saying that delta H is more exothermic or more negative, and that's then unambiguous, and you get the marks. Part B then is about bond enthalpies, and first it wants the definition again. So the bond enthalpy is the enthalpy required to break 1 mole of bonds in the gas phase. Those are the 2 key points you need. So it's 1 mole of bonds. It's always 1 mole in these kind of definitions. And it's breaking them. That's the key thing, not making them. So one enthalpy change when you break 1 mole of bonds in the gas phase. The average bit relates to the fact that these things are generally averaged over a range of compounds. So for OH, for example, it might include an OH bond in water, but also an OH bond in an alcohol, or an OH bond in a carboxylic acid, and they'd all be slightly different. So that's what the average bit relates to, but you don't need to include that in the definition. So it's just the enthalpy change when 1 mole of bonds are broken in the gas phase. So then we come to the calculation. The safest way to make sure you get this right is to draw out the displayed formulae of these compounds, because that way you don't miscount the bonds. Obviously you don't have to do this. If you're confident you can do it without, you could save a little bit of time, but this is the safest way to do it. So you can just rewrite this equation and say, right, we've got 2 F2s, so there we are, and we've got 2 H2Os, and if you draw them out like this, the point is you can then see every bond, and that's going to make sure that you don't fail to count them. So you've got O2 on that side, and then 4 HFs. Right, so then we can go through, and the trick is that you want to add up the 2 sides separately. It's a good idea to do that because in the mark scheme very often you get separate marks for the two. So if you just mess up one of them, if you've given separate subtotals, you'll still get some marks. So in this case, we have two F2s. So that's 2x, because F2 is the one we don't know. So we're going to say x is the bond enthalpy for F2. And we're breaking 1, 2, 3, 4 OH bonds. So 2x plus 4 lots of OH, so 4 times 464 gives us the number on that side, and that works out to be 1856. So 2x plus 1856 is the total bond enthalpy on that side. On this side we have an O double bond O, so that's 498, plus 4 lots of HF, so 4 lots of 568, which adds up to 2770. And now we've got to combine those. So the crucial thing is that you remember that these bonds are being broken, and that being broken is endothermic. You have to put energy in to break bonds, and endothermic is positive, so it's plus that number. So we get plus 2x plus 1856 is the contribution from these bonds. These bonds are being made, and when you make bonds you give out energy, so that's a negative exothermic contribution. So minus 2770 equals the overall enthalpy change, and we know what that is because it told us in the question that that's equal to minus 598. So we can just rearrange that to solve for x. So we get that 2x is equal to minus 598 minus 1856 plus 2770, which is equal to plus 316 kilojoules per mole, and therefore x, which is equal to the FF bond enthalpy, which is what we want, is just half of that number. So it's plus 150, 158, sorry. Thought I'd messed that up for a second. Plus 158 kilojoules per mole is the right answer. So you just got to be careful about the signs and be careful that you don't miss any of the bonds out.